In this series of lectures, I am going to describe the perturbation theory in quantum mechanics, both the time-independent and the time-dependent versions. Perturbation theory, of course, is a very important part of the calculational tools in quantum mechanics for the simple reason that most quantum mechanics problems that are of any importance cannot be solved exactly. Perturbation theory is one very important way of getting controlled approximations to the final answer in such situations. So let us start by describing the setting for time-independent perturbation theory. This essentially involves the problem of finding the spectrum, which means eigenvalues and eigenvectors, of the Hamiltonian operator H. Most often, perturbation theory is couched in the language of the spectrum for the Hamiltonian, although you must realize that you should be able to use similar ideas for other Hermitian operators as well. But be that as it may, we are going to talk about the spectrum of the Hamiltonian here. And H, this Hamiltonian, the Hamiltonian for the full system, presumably has eigenkets psi n and corresponding to energy eigenvalues En. Now, our aim is to figure out what the ket psi n's and En's are, given that we can decompose this Hamiltonian H into two pieces, H0 and V, where the spectrum of H0 is exactly known. So, H0 is an so-called exactly solved Hamiltonian. So, its eigenvalues are epsilon n in my notation, and the corresponding eigenkets or eigenvectors are phi n. So, we know the epsilon n's and phi n's exactly. V, the rest of the Hamiltonian, is in some sense small. That is, we expect at least that because of this additional piece V, the eigenvalues and eigenvectors of H will differ from the eigenvalues and eigenvectors of H0, but not by a huge amount. So, perturbation theory essentially allows us to calculate corrections due to this perturbation V to the unperturbed eigenvalues epsilon n and eigenkets phi n. So, we want to figure out how psi n's are different from phi n's and how En's, the exact eigenvalues of H, are different from epsilon n's. Now, to solve H psi n equals En psi n, what we do is we first introduce a formal parameter lambda by writing H as H0 plus lambda V. Of course, this means that when lambda is 0, we have our exact problem, that is H0 whose solutions we know exactly, and our actual problem, the problem which we really want to solve, is the one for lambda equals 1. Here lambda is really a formal parameter. It's meant to keep track of how many times V is appearing in a result. Now, in the Rayleigh-Schrodinger perturbation theory, which we are describing right now, we make a basic assumption. The basic assumption is that the energy eigenvalues and eigenkets of the full Hamiltonian can be expanded in a power series in lambda. En is En0 plus lambda En1 plus lambda square En2 and so on. Notice that these 0, 1, 2 up here are not powers. So that's why I have just written them in brackets to remind you that this is not En to the power 0, En to the power 1 and so on. These are just the 0th order, first order, second order corrections to the unperturbed energy eigenvalue. Of course, you can write this using the sigma notation in this form as lambda to the m, Enm, where m runs from 0 all the way up to infinity. Well, we assume that psi n can be expanded in a similar manner. So, the ket psi n is the ket psi n 0 plus lambda psi n 1 plus lambda square psi n 2 plus and so on. So, it's a series, infinite power series in the parameter lambda with terms psi n 0, psi n 1, psi n 2, etc. These are all first order, second order, and so on, corrections to psi n 0. So Schrodinger equation for H, this H0 plus lambda v, simply becomes H0 plus lambda v acting on this infinite sum, which is psi n, equals this infinite sum, which is of course En, times this infinite sum, which is psi n. So if I just were to write this out in detail, this is what it would look like. H0 plus lambda v acting on psi n0 plus lambda psi n1, etc., etc., is equal to En0 plus lambda En1 plus lambda square En2, and so on. Now you can see the utility of this lambda parameter, despite the fact that we are going to put in lambda equal to 1 in the end. The parameter lambda gives us a very nice way of looking at this equation order by order. So if this is going to be an identity in lambda, it has to match for all parts of lambda. So you can compare powers of lambda on both sides. Say the term which is completely independent of lambda, that is the term which has the power lambda to the power 0, on the left is simply H0 acting on psi n 0. Every other term on the left hand side has at least one lambda power. What about on the right? On the right, the lambda independent term will be En0 times the ket psi n 0. So this is the equation we get by comparing lambda to the 0 on both sides. By comparing lambda to the 1, well, you get lambda to the 1 in two ways on the left hand side. You get it from H0 acting on psi n1 and V acting on psi n0. That's the left hand side. What about the right hand side? You get lambda to the 1 by taking En0, which has no lambda, times psi n1, which has exactly one lambda with it, plus En1, 1 lambda, times psi n0, no lambdas. So matching them both, this is the equation that you get from the first order perturbation term, lambda to the 1. Well, what about lambda to the 2? Well, on the left you get H0 psi n2, that gives you lambda square. Another term which gives you lambda square is V psi n1. What about the left hand side? That was the left hand side, sorry. What about the right hand side? You get En0 psi n2 lambda square. En1 already has one lambda, that goes with psi n1 to give you lambda square, and En2, which already has all the lambda powers you need for lambda square, gets paired with psi n0. So for lambda square, this is the equation that you get. Well, for lambda cube, similarly on this side you get H0 psi n3 plus V psi n2, that gives you the 2 lambda cube terms on the left. There will be 4 lambda cube terms on the right, En0 psi n3, En1 psi n2, En2 psi n1, and En4 psi n0. And we can go on like this. In general, for lambda to the m, the mth order perturbation equation in Rayleigh-Schrodinger perturbation theory is H0 acting on psi n_m plus V acting on psi n_m minus 1. So on the left you get only 2 terms, simply because there are only 2 terms in this H0 plus lambda V. On the right, on the other hand, you actually get m plus 1 terms. En0 goes with psi n_m to give you lambda to the m, but En1 goes with psi n_m minus 1, and so on, all the way down to En_m going with psi n_0. So these are the basic equations in Rayleigh-Schrodinger perturbation theory. Now let us focus on these equations, at least the first few of these equations, term by term. The 0th ordered equation is pretty straightforward. It says H0 acting on psi n_0 is En0 psi n_0. Of course, this is nothing but the eigenvalue equation for the unperturbed Hamiltonian H0. And this should of course not come as a surprise, because when lambda is 0, H does reduce to H0. And so it's understandable that the 0th order term in the perturbation expansion, the only term which actually survives when lambda is 0, is the same as the eigenequation for H0 itself. And this equation obviously shows that En0 must be an eigenvalue of the unperturbed Hamiltonian H0. This, after all, is an eigenvalue equation. Now, which eigenvalue is this? Could have been any one of them. So, let's say we label things in such a way that En0 corresponds to the eigenvalue epsilon n. So, we have already assumed when we wrote down the notation that there is a way in which I can order the eigenvalues, maybe in ascending order. Of course, ascending order only works when there is no degeneracy. For eigenvalues with degeneracy, we will have to sort of figure out some other way of counting them, putting them in order. But the point is, epsilon n is an eigenvalue for H0, and we are now looking at how this particular eigenvalue changes when you switch on the perturbation. So, En0 we are taking to be epsilon n. Now, we can have one or two cases. This eigenvalue epsilon n of H0 may be non-degenerate with eigenket phi n. That means all eigenkets corresponding to epsilon n are either phi n or a multiple, which essentially means phi n. So, that's one possibility. In this case, if that happened to be the case, then it's easy to identify what psi n0 is. Psi n0 has to be phi n up to an overall constant which doesn't matter. So, when we are dealing with a non-degenerate energy eigenvalue for the, remember when I say non-degenerate, I mean non-degenerate for the original unperturbed problem. If you have an energy eigenvalue which is non-degenerate, then starting off the perturbation theory for that is relatively simple, because psi n0 is something you already know, it's phi n, the corresponding eigenvalue. Of course, it could be that epsilon n is not non-degenerate, it's actually d-fold degenerate, where d is an integer more than 1. And let's say the corresponding eigengets are phi n1, phi n2, phi n3 up to phi nd. Then this equation where with En0 equal to epsilon n cannot really tell me what psi n0 is. All it can tell me is that the ket psi n0 has to be some combination of phi n1, phi n2, phi n3 up to phi nd with possibly complex valued coefficients C1, C2 up to CD, which we do not know as yet. At least the 0th order perturbation equation will not tell you what these coefficients C1, C2, CD are. So, from this point on, our treatment takes two slightly different routes. If we have a non-degenerate energy eigenvalue, what we resort to is what is called non-degenerate perturbation theory. That's simpler to begin with for the simple reason that the unperturbed wave function psi n0 is exactly identified already as the ket phi n, eigenket of H0 corresponding to epsilon n. On the other hand, if epsilon n happens to be degenerate, we have to go in for degenerate perturbation theory, where the problem is that at least at this stage, we don't even know what the unperturbed energy eigenfunction is. So, degenerate perturbation theory will be described in a later lecture. For the time being, let's look at non-degenerate case, which is the easier one. So, in the non-degenerate case, of course, this equation, the 0th order equation that we have just been discussing, immediately tells us that En0 is one of those energy eigenvalues, epsilon n. Psi n0 has to be the ket phi n, the eigenket corresponding to epsilon n. Let me point out that for the same Hamiltonian H0, some energy eigenvalues may be non-degenerate, some other eigenvalues may be degenerate. So, it's not as if degenerate or non-degenerate perturbation theory designation is for a particular system. The particular eigenvalue you're looking at, that decides whether you have to use degenerate perturbation theory, something we are going to describe a bit in a later video, or non-degenerate perturbation theory, the one I'm talking about right now. So, of course, if we are doing non-degenerate perturbation theory, then our equations are the same as the ones we have already had. We have already seen the lambda to the 0 equation, so we are only interested in the rest, lambda to the 1, lambda to the 2 and so on. And the important thing is, the only thing that really changes, instead of v psi n 0 here, we can put in phi n. We already know what the eigenket is. Instead of the en 0 which was sitting here, I can put in epsilon n. So you had a0 psi n 1 plus v psi n 0 on the left, en0 psi n 1 plus en1 psi n 0 on the right. So I've changed this to epsilon n here and phi n here, and I've done that to all the equations here. Basically, on the right hand side, the very first term had an en0 always, so that gets changed to epsilon n. The last term had enm psi n 0, that's changed to phi n. Okay, so now let's go on to see what these equations tell us about the energy corrections En1 and the wave function corrections, so the eigenket corrections psi n1 and so on. So now let us look first at the first order energy correction. For that, we start from the equation which came from comparing the lambda to the 1 on both sides of the perturbation equation. This of course is the equation where we have already put in psi n 0. We are sitting here and here as phi n, and en 0 is epsilon n. So our job is to try to find out en1. Now that's actually very easy. All you have to do is apply the bra phi n from the left on both sides of the equation. So the bra phi n comes and sits in each one of these terms here. The rest of course is whatever you had in this equation. Now remember, the ket phi n is an eigenket of H0, and since H0 is Hermitian, bra phi n acted upon by H0 is the same as bra phi n acted upon by H0 dagger. That's the adjoint of H0 acting on ket phi n, and since epsilon n, the eigenvalue, has to be real for Hermitian operators, you end up with this term being epsilon n H0, epsilon n phi n psi n1. Actually, the first term on the right hand side is also exactly the same, so they cancel. We are left with phi n v phi n, and here of course en1 is just a number, it comes out, and phi n, this overlap is just 1. So we have already assumed, by the way, maybe I should have mentioned this, but I took it for granted, that for the unperturbed energy eigenkets, the phi's, we have already assumed them to be a complete orthonormal set. Okay, but now that we have done that, it's easy to read off what the first order energy correction is. Simply, the expectation value in the unperturbed eigenstate phi n of the operator V. It's sort of easy to understand this. It just says that to a first order in perturbation theory, the energy correction for non-degenerate energy eigenvalue is simply nothing but the expectation value of the perturbation operator in the unperturbed state. So this is a very, very important result which we will use in applications over and over again. What about psi n1, the first order correction to the eigenket? Well, for that, we start with the equation, the same equation all over again, but this time instead of hitting with the bra phi n on the left, what I will do is hit with the bra phi m, where phi m could be any arbitrary energy eigenbra for the unperturbed Hamiltonian. Not necessarily the same eigenbra as the one corresponding to the energy eigenvalue we are dealing with. The calculation goes more or less the same way. Phi m is 0, of course, is simply epsilon m times bra phi m, and here of course the epsilon n and the en1 being numbers just come out of these matrix elements. So you end up with this result. Now just as a quick check, if you put in m equal to n, what happens is this term and this term just cancel each other out. Right? Because now that m is equal to n, epsilon m and epsilon n are exactly equal, and this term simply becomes phi n v phi n, this term becomes 1, so we get back the result that we had in the last slide. En1 is phi n v phi n. For m not equal to n, what happens is this term goes away, right, because delta mn now is 0. So this tells me how to find out the overlap of psi n1, our first order energy eigenvalue correction, with the phi m. And how much is that? You just move this to the other side and divide, and you end up with this result. Phi m v phi n divided by epsilon n minus epsilon m. Notice that our energy eigenvalue epsilon n is non-degenerate, so it does not match any of the other energy eigenvalues. So this division by epsilon n minus epsilon m is fine. You are dividing by a non-zero number here. So this gives me the overlap of psi n1 with phi m. Now, I already know that the phi m's form a complete set. So if I know the overlaps of psi n1 with every one of the phi m's, I essentially know what psi n1 is. There's only one catch. The catch is, this formula tells me nothing whatsoever about the overlap of phi m and psi n1 when m is equal to n. Of course, when m is equal to n, this side diverges, but you already know that when m is equal to n, this equation tells me nothing about phi and psi n1, because phi and psi n1 just drops out of the equation. So with this in mind, psi n1 turns out to be this expansion phi m times the phi m psi n1 overlap value, which is phi m v phi n by epsilon n minus epsilon m. From here, for m not equal to n, but we are left with one more term, phi m psi n1 times the ket phi n. Perturbation theory, it is first order perturbation theory, will not tell us what this term is. So we have found out that the first order energy correction is simply the expectation value of V in the unperturbed energy eigenstate. The first order wave function correction is also pretty straightforward, except for the fact that there is an unknown undetermined piece here. Now, can we find out this piece by demanding something else about the wave function, like demanding that it's normalized? Perturbation theory cannot determine this term, that's clear. So can we use normalization for this? Well, that depends, in the sense that some authors use what is called intermediate normalization. They demand that all these first order, second order, third order wave function corrections, they are orthogonal to the unperturbed phi n. This is what they demand, which means phi n psi n1 in particular. This is for phi n psi n s for any s. Phi n psi n1 is 0. Of course, this is for s mode 1 or more. Psi n 0 of course is the same as phi n, and then the overlap would simply be 1. But for all other, for the corrections, psi n1, psi n2, etc., the demand is phi n is orthogonal to them. So this term simply drops out if you use the intermediate normalization convention. However, many other authors, including the rest of this lecture, for example, we use a more conventional normalization. Okay, this is what you get when you demand the intermediate normalization. So, sorry, the conventional normalization has just escaped below the screen. Demanded here in the equation, which is invisible to you right now, is that the perturbed wave function, the entire perturbed eigenket psi n, is normalized to 1. So this is what we are really demanding. Psi n, the eigenvalue which, remember, can be expanded in powers of lambda like this, where psi n1, psi n2, etc. the first order, second order corrections. We are demanding that this psi n is normalized to 1. Of course, if you were to normalize this, that means you take the overlap of this with itself, and because lambda is real, it stays lambda when you take the adjoint, but it of course changes, the sum index changes from m to m prime, and if you do it carefully enough, this is what you end up with. Now there is a sum over both m and m prime, but notice that the power of lambda here is m plus m prime. We can change our indices here and change indices from m plus m prime. Let's change that to s. So we switch over to new indices s, which is m plus m prime, and the index j, which now runs from 0 to s. And of course, this is lambda to the s, and when this first coefficient is j, the next one has to be psi n s minus j, so that the two together add up to s. And this of course is 1, which is the same as lambda to the s delta s0, this power series. Now only the s equal to 0 term, which is lambda to the 0, namely 1, survives on the right hand side. Everything else goes away. And just comparing them term by term gives us this as a normalization condition. So if you use the conventional normalization here, the condition that you have to follow is a bit more complicated. Let's just see what this means. This works for all s, 1, 2, 3 and so on, even for 0, but for 0 you have to get 1, and that's pretty straightforward. If you have s equal to 0, there's only one term here, psi n 0, psi n 0 again, which is phi n's overlap with phi n, which we know is 1. For s equals 1, what this becomes is psi n 0, which is phi n, psi n 1, plus psi n 1, psi n 0, that is psi n 1, phi n. So notice that in the conventional normalization, we don't really get the result that phi n psi n 1, this unknown piece in psi n 1, which perturbation theory cannot tell you about. We don't get that as 0. All we get here is that it, when added to its complex conjugate, is 0, which means it has to be purely imaginary. That's all you really get. For s equal to 2, you get something slightly more complicated. You get phi n psi n 2 plus psi n 1 psi n 1 plus psi n 2 phi n. Remember, phi n is psi n 0. So this is really psi n 0, psi n 2, psi n 1, psi n 1, psi n 2, psi n 0. All the three ways you can add up to non-negative integers and get 2. Of course, for s equal to 3, it will be psi n 0, psi n 3, psi n 1, psi n 2, psi n 2, psi n 1, plus psi n 3, psi n 0. 4 ways and so on. And this has to be 0. So this one, for example, tells you that the imaginary part of phi n psi n 2 is related to this overlap psi n 1, psi n 1, and so on. Now let us take a look at the second order correction. Well, we start from the second order equation, the equation you get from lambda square. What you get is h0 acting on psi n 2 on the left, plus v, which has only one lambda, times psi n 1 acting on psi n 1. All on the left, these are the two terms you get. These are the two terms which will give you lambda square. On the right, three terms give you lambda square. En0, which we now know is epsilon n, psi n 2, En1 times psi n 1 plus En2 times phi n. So aim here is to find out En2. Well, let's start by hitting both sides by the bra phi m. Right? If you do that, the right hand side is pretty easy. All these numbers, epsilon n, En1, En2 are just numbers. They come out and you directly end up with overlaps. On the left, this one becomes epsilon m times phi m. So this is also a simple overlap. And if I just move this term, which is epsilon n phi m psi n2, to the other side, you end up with epsilon m, which came from here, minus epsilon n, which came from here, phi m psi n2 plus phi m v psi n1 equals en1 phi m psi n1 plus en2 delta m1. Now, to find out en2, all you have to do is put in m equal to n. In fact, we could have done that at the very beginning. If I do this, then this phi m psi n2 term just drops out. By the way, if you want to now know what psi n2 is, find out the second order eigenfunction correction, you will actually need to know what these overlap values are. And for that, all you do is put m naught equal to n. And this term en2, the unknown en2 will drop out. And then you will be able to find out phi m psi n2. For the time being, we want to find out en2, put in m equals n. Then because of this factor, this unknown term drops out and you are left with en2 is simply phi n v psi n1 minus this term en1 phi n psi n1. Of course, if we were using intermediate normalization, phi n psi n1 would be 0, so this term would simply not be there. Now this looks like a bit of a problem because, as we said a while ago, phi n psi n1, what this overlap integral is, this particular one, the one corresponding to m equal to n, cannot be found from perturbation theory. So it looks like our formula for the second order energy correction has a piece which perturbation theory simply cannot tell you about. So how then can we claim that perturbation theory allows us to calculate the energy correction? I have a nice formula for en2, but there is a piece there which cannot be found out by perturbation theory itself. In fact, the intermediate normalization told us if we were to adopt that, this would be 0, but that would just be a convention. Real measurable values like energy eigenvalues should not depend on which convention you are following. And if we use the conventional normalization, then phi n psi n1 is not even 0, it's a purely imaginary number. Of course, that should also give us some reason to worry. After all, en2 is a second order correction to a purely real quantity, the energy eigenvalue en. en1 is also real, right? It's just the expectation value of v, a Hermitian operator, in the state phi n. So this looks like a purely imaginary term and should not have any place in an expression for en2, which should be real. So let's see whether we can resolve all these issues. Two issues are there really. One is that this unknown thing, something which cannot be determined by perturbation theory, is there in a formula for calculating second order energy correction. That in itself should be a problem, and it's perhaps an even, well, not even bigger, but at least a problem of the same magnitude, that if we were using conventional normalization, then this term will be purely imaginary, and you apparently have a purely imaginary term in something which should be real. Well, to understand this better, what we do is use a resolution of the identity. Remember, the ket phi m's are assumed to form a complete set of orthonormal vectors. So this is the identity, and we just insert the identity in this expression. This is exactly the same expression as the one up here, except that we have inserted the identity in between v and psi n1. This of course breaks up into this space phi n v phi m psi n1, where the sum over here is over all m. Of course, from this you have to subtract this troublesome term that we have been worrying about. Now notice that this whole sum can be split into two pieces. The piece where m is not equal to n, majority of the terms of course, that's just this term here, plus one more piece where m is equal to n. But what is it when m is equal to n? Phi n v phi n psi n1. So we club that along with this term and take this factor common, I end up with this result. And now we see why this troublesome term does not really cause us any bother whatsoever. Phi n v phi n we figured out a while ago is nothing but En1. So this term is really 0. So the fact that we could not figure out what phi n shine 1 was from perturbation theory actually has no bearing whatsoever in the final result for En2. The final result is independent of this extra piece. And we are left only with the m not equal to n term. Now we use the fact that we already know what these overlap values are. Remember, we know them only for m not equal to n. I plug this in. Notice phi n v phi m may very well be a complex number. Phi m v phi n could also be a complex number, but these two complex numbers are conjugates of each other. So their product, of course, is a modulus square, which is definitely a real number. So this is the final result for the second order energy correction. The mnth matrix element of V, this bra phi m v ket phi n, the magnitude squared of that goes in the numerator of the expression. The denominator just has epsilon n minus epsilon m, the energy difference between the other states which are there in the sum and the unperturbed energy eigenvalue epsilon n. So some remarks here. Up to second order in perturbation theory, En simply turns out to be epsilon n, which is of course, here we are putting back lambda equals 1. So we have the full Hamiltonian H equal to H0 plus V. The nth energy eigenvalue En turns out to be epsilon n, which is of course En0, plus Vnn, which is En1, plus Vmn mod square by epsilon n minus epsilon m summed over all m not equal to n, where Vmn of course is nothing but this shorthand, and Vnn of course is phi n v phi n, the expectation value in the nth energy eigenstate. Now when is the second order correction important? Well, if the first order correction vanishes, of course the second order correction becomes all important. Even if the first order correction did not vanish, the second order correction could become pretty big. Remember, Vmn's in general are matrix elements of the perturbation V, and we are assuming that in some sense V is small compared to H0. So in most cases, V's are small compared to the epsilons, the Vmn's. Which is why this second order term, which has square of such a matrix element, would typically be much smaller than the first order term, which has only one Vnn. Of course, if the first order vanished, as we just said, this would have to be important, because then that's the lowest non-trivial correction you have. But there's another situation when this term might become very important, which is when you have a nearly degenerate energy level, that is epsilon m is pretty close to epsilon n. Then you have a very small denominator here for at least that term, and then this sum, at least a few terms of that sum, even if only one term, might become a pretty important big thing. So when you're close to achieving degeneracy, when your spectrum is close to being degenerate, the second order correction may become very, very important. Of course, if you have exact degeneracy, then epsilon n minus epsilon m will be 0, but then you will not be able to use this method that we have been using so far. You will have to modify the method a bit. So if there is a different energy level very close to epsilon n, the second order correction may become very important. So in many practical applications, it so happens that for most of the regime you can actually ignore the second order term, but suddenly the second order term becomes important because you're getting close to a degeneracy. And there, this can have all kinds of interesting physical effect. Now, another result that we get is if you consider the ground state, where n is 0, the second order energy correction is Vm0 mod square by epsilon 0 minus epsilon m summed over all m, which is not 0. Sorry, this should be m not equal to 0 here. Now, notice that for all m which are not 0, epsilon m is actually more than epsilon 0. After all, epsilon 0 is the ground state energy. Any other epsilon is more than that. which means that every term in this sum is negative, and so for the ground state the second order energy correction is always negative. That's another important point. And the point that we have been stressing, the indeterminacy in the first order corrected wave function psi n1 does not affect the value of n2. And not only that, if we try to find out psi n2 just by using the same technique as before, instead of putting m equals n, use m different from n, and we get phi m psi n2 and so on, we will see that there are certain terms that you cannot find. But this lack of knowledge about certain terms will not lead to any problem when you try to calculate En3 or En4 or so on. Not only that, it can be shown with a bit of effort that not only does this lack of knowledge about certain parts of the corrected wave function not make a difference to the energy eigenvalue calculations or correction calculations, they will not make any difference in physical expectation value calculations as well. So the fact that we cannot figure out certain pieces of the wave function from perturbation theory will make no physical difference whatsoever. So far, we have discussed perturbation theory in the abstract. The formulae that we have derived so far can be used for any system where you have a large, exactly known Hamiltonian and a small perturbation. Let us now round off this lecture with an example of a calculation where we can sort of gain some experience and confidence in what I have been talking about so far. Now, the problem that we are talking about here is the perturbed harmonic oscillator. As you can see, perturbed is being written within quotes here, and you can easily understand why. Our system has a Hamiltonian H, which is of course as usual H0 plus V, where H0, the exactly solved Hamiltonian, is our familiar harmonic oscillator Hamiltonian, p hat square by twice n plus half m omega square x hat square. The perturbation V is actually of the same form as the potential energy in the harmonic oscillator Hamiltonian. It's given by half m alpha square x hat square. So it's very easy to see that the actual Hamiltonian here is really one which is still a harmonic oscillator Hamiltonian, just with the omega being replaced by omega prime equal to omega square plus alpha square square root. So in this case, the unperturbed solution, the solution to the unperturbed Hamiltonian, there is a spectrum of H0 phi n equals epsilon n phi n, is of course well known. The epsilon n are the energy eigenvalues of the unperturbed harmonic oscillator. As you all know, the energy eigenvalues is h cross omega times n plus half. And phi n are the standard eigenkets, the number eigenkets of the operator A dagger A. Again, very familiar stuff. Now the exact solution to this particular Hamiltonian is known. That is why perturbation theory is being applied here, well, within quotes, so to speak. Since we know the exact answer, we can compare this with our perturbation theoretic results and see whether we are actually making good progress or not. In the exact answer, the energy eigenvalues are exactly of the same form as the unperturbed energy eigenvalues, except that omega has to be replaced by omega prime, the actual angular frequency of the full harmonic oscillator that we are dealing with, and therefore the energy eigenvalues turn out to be h cross square root of omega square plus alpha square times n plus half, where n, of course, as you all know, goes from 0, 1, 2 and so on. Now, in order to see the connection between this result and our perturbation theoretic result that we are going to derive soon, let us actually try to write this in the form of a perturbation expansion in the parameter which describes the perturbation, namely alpha square. To do that, all I have to do is take omega out of the square root, write the square root of 1 plus alpha square by omega square using the binomial theorem for fractional indices. And I've just written down the first 3 terms of this expansion. Of course, there are infinitely many more terms to come. And in these 3 terms, the first one has a single power of alpha square. Remember, alpha square is what exactly is in the perturbation. And the second one has 2 powers of alpha square. So these are obviously terms which correspond to first order correction in perturbation theory and second order correction in perturbation theory respectively. Let us just see whether our perturbation theoretic calculations actually give us exactly these terms or not. To carry out the perturbation theoretic calculation of the energy corrections, what we need is the matrix element Vmn, which is the matrix element of V sandwiched between the unperturbed energy eigenkets, the number eigenstates m and n. And the easiest way to do the calculation is to rewrite the perturbation V in terms of the raising and lowering operators for the harmonic oscillator. This is of course familiar to all of you. I will just briefly remind you that the lowering operator is given by this expression, root over m omega by twice h cross x plus ip by m omega. This of course is the lowering operator for the unperturbed Hamiltonian. So here you have the omega, the unperturbed frequency sitting in the expression. A dagger of course is nothing but the adjoint of this expression. And by solving these two for x and p, it's easy to see that x and p are given by root over h cross by twice m omega a plus a dagger. This is the one we are going to need here. And root over h cross m omega by 2 a minus a dagger by I. So putting the expression for x back in the potential energy term, what we get is simply this. Half m alpha square of course is the prefactor and x hat square is given by this quantity. And just by rewriting things a bit, I get h cross omega by 4 times alpha square by omega square times a plus a dagger whole square. So what we need are matrix elements essentially of a constant times a plus a dagger whole square. And the calculation of the matrix element is simplicity itself. You are sandwiching a plus a dagger whole square between the bra m and the ket n. Expanding out a plus a dagger whole square gives you a square plus a dagger square plus a dagger a. And then using the standard theory of raising and lowering operators in the harmonic oscillator, you know that this matrix element, for example, m a square n, will be given by m a square n. In order to figure that out, remember that a acting on n gives you root n minus 1. So this is root n times m. 1a has already acted on n, so this is m a n minus 1. Then a acting on n minus 1 gives you root n minus 1, n minus 2. So root n into n minus 1, m n minus 2. This of course is trivial and all of you have surely done this lots of times. And since the number eigenstates are orthonormal, this has to be delta m n minus 2. And that's exactly what is the first term here. Very similarly, a dagger square's matrix element can be easily figured out to be this. And a dagger plus a dagger a. This of course is nothing but twice n hat plus 1. So acting on the ket n, it returns twice n plus 1, the number, times the ket n. And you are left with the bra m ket n overlap, which is of course delta mn. So this is Vmn, that the quantity that we need to continue our calculation for the perturbations, to calculate our corrections to the nth energy level. It is nearly trivial to calculate the first order energy correction here. En1 is simply Vnn, that is this expression where m is equal to n, and that means this term and this term drops out. You are left with just twice n plus 1 from this term. And when you combine everything together, in particular if you take the h cross omega by 4 across the alpha square by omega square and multiply into 2n plus 1, you can rewrite this expression in this form. I've deliberately written this expression into this prefactor times h cross omega n plus half, just to remind you that this is exactly the form we had for the exact energy eigenvalue, at least up to first order in alpha square. So let's go back a bit and let me show you where this was earlier. This was our exact solution. So apart from h cross omega n plus half, which is of course epsilon n, the unperturbed energy eigenvalue, the first order correction, remember alpha square is what is there in the perturbation. So the first order in perturbation means one factor of alpha square will be half alpha square by omega square into h cross omega n plus half, which is exactly the result that we had obtained here. The next order of the perturbation should give me minus 1/8 alpha to the 4 by omega to the 4 times h cross omega n plus half. Let's check whether that is exactly what we get. To calculate En2, the second order correction, what we need to do is evaluate this sum. Vmn mod square by epsilon n minus epsilon m summed over all m other than m equal to n. So that means what we need to do is take this expression. Remember, epsilon n minus epsilon m is just h cross omega into n minus m. So you can rewrite it this way. And what you need to figure out is what this infinite sum is. Although the sum is an infinite one, only very few of the terms is non-zero. In fact, if you look at the Vmn expression, you know that the only non-zero terms are for m equals n minus 2, which is this one, and for m equals n plus 2, which is this one. The m equal to n term, of course, is also non-zero, but that is not there in our sum, and which is a great thing because that would have had a zero denominator. Now, apart from these things which you see here, you have this prefactor which you have to square, and n into n minus 1 square root also gets squared, so does this. And putting all of this in together, what you get is this. This is the prefactor that we had, square of the prefactor, of course. This is square root of n into n minus 1 whole square, of course n into n minus 1, divided by n minus m. In this case, this, remember, is when m is n minus 2, so you have a 2 in the denominator. You get n plus 1 into n plus 2 from the square of the matrix element. When m is n plus 2, so you get minus 2 in the denominator for that. And once you just carry out the simple algebra here, you will end up with this expression. Minus 1/8 alpha to the 4 by omega to the 4 times h cross omega n plus half. Of course, no surprises there. This is exactly what we expected from our exact solution. This was, of course, a warm-up problem. There was really no point in using perturbation theory for this particular problem because we knew the exact answer anyway. But as was the case for the variational method, solving a problem for which the exact answer is known by an approximation technique gives us some confidence in the applicability of that particular technique. What we are going to do in the next lecture is take a look at a more non-trivial problem, that of an harmonic oscillator, where we are going to look at how the presence of a quartic perturbation is going to change the energy levels and eigenfunctions of a harmonic oscillator. We are going to take a look at a trick which is going to make the higher order correction calculations for energy eigenvalues somewhat easier. But that is for the next lecture. Until then, goodbye.